So today we are going to be talking about phase changes part 2. We're going to discuss phase changes and pressure. Before we start talking about how phase changes relate to pressure, let's discuss what pressure is. So pressure is simply the amount of force that's being exerted over a given surface area. So if you think about taking your finger and pushing down onto your desk or onto your arm, you are applying pressure over a certain area. Now, if I increase the amount of force that's being applied, I'm increasing the pressure. And if I decrease the amount of area over which that force is being applied, I also increase the pressure that's being applied. And if you recall from our first lesson on phase changes, temperature is one factor that affects phase change. Pressure is the second factor involved in phase changes. And today we are going to discuss how. So first, let's talk about how pressure relates to the phase of matter that matter is existing in. So we know that as thermal energy is added to a substance, so as I increase the temperature of a substance, its particles begin to move further apart, they begin to move further, and they begin to move faster. Eventually, as more and more thermal energy is added, eventually they move far enough apart and they begin moving at a high enough rate of speed that they will eventually transition into the gaseous phase. So along that line of thought, and if you look over here in the diagram, in the gaseous phase, the particles of a substance are moving very, very fast. They're moving very far and totally at random, which is causing them to collide with one another and the particles in surrounding matter at very high rates and at very high amounts of force. This results in an increase in pressure in substances in the gaseous phase than in the liquid and the solid phase. So simply put, when a substance is in the gaseous phase, it is at a higher pressure than it is in a liquid or solid phase. And again, that is due to the motion, the speed of its particles, and the collisions that they are making with each other and with the molecules in surrounding matter. So if we see here, I've actually inserted a GIF that can show you what this looks like. So particles in the gaseous phase, you see here, constant, fast, random movement. Lots of collisions are taking place with these particles as they move, both with each other and with whatever matter is surrounding them, which, again, if we think about what pressure is, applying force over a surface area is causing these to be at a higher pressure. Now, if we think back to thermal energy and pressure, these are also positively correlated. So as thermal energy is added into a gas, its particle speed and kinetic energy will continue to increase along the same pattern that we've been discussing. With more thermal energy comes more kinetic energy to particles, faster speed at which they move. This tells us that as thermal energy is added into a gas, its pressure will also increase. It also goes to say that the inverse is true. If thermal energy is removed from a gas, or if the gas is allowed to cool, those particles' speed will decrease, their kinetic energy will decrease, those collisions will decrease, and hence pressure will also decrease. So some examples of this, I know it's a lot, so let's take this into the real world. Something you may have actually experienced is either a ball, doesn't have to be a basketball, any type of ball, or even a bike tire or a balloon. If you possibly have ever left one of these outside or in the car during the winter, you may have noticed that a basketball or a balloon or even a bike tire that seemingly just a few hours before was completely inflated may have become much less inflated, might have become a little bit flat, or the balloon might just look very deflated. Well, that is because of what we just discussed. So inside of that balloon or that ball or that bike tire is air molecules in the gaseous phase. When they are left outside or in a cold vehicle, what we now know to be true is that those particles will lose kinetic energy, causing that pressure to decrease. Pressure is what keeps that ball inflated or those balloons inflated. So as those gas particles slow down, they stop moving, they stop having so many collisions with themselves and surrounding matter. You will actually see the result in the deflation of the ball or the balloon or whatever other inflated object you might be looking at. Finally, we are going to talk about how pressure relates to phase changes. So you may not know this, but no matter where you are on Earth or anywhere, a substance always has pressure being exerted on it by its surroundings. So in our case, on Earth on a regular day, that's the atmospheric pressure from the atmosphere surrounding us. So we always are having pressure exerted upon us by our surroundings. So normally on Earth, that pressure is constant. It doesn't change. It's actually called atmospheric pressure, and it's a constant value. However, if we were at different locations or under different conditions, to change the amount of pressure that a substance is under, phase changes happen differently. So if we think about a substance that is being exposed to lower pressures, matter will tend towards less condensed phases. So there's less pressure pushing down on the matter, so to speak. It is more inclined to move towards the liquid or the gaseous phase. You can think about if not as much pressure is pushing those particles together, they are simply more inclined to spread out, move apart, and move towards the gaseous phase. This means that at these lower pressures, less energy is required for the transition from a liquid into a gas. Therefore, the transition from liquid to gas or evaporation will happen at lower temperatures. You will not need to input as much thermal energy in order to undergo the transition from liquid to gas. The inverse is also true at higher pressures. So at higher pressures, again, you can think about the pressure simply pushing down harder on these particles, keeping them more condensed, so tending more towards the liquid or the solid phase. For this reason, more energy is required for the transition from a liquid to a gas, meaning in order to cause a liquid to evaporate or transition to gas at higher pressures, more thermal energy will be needed. Therefore, that evaporation will happen at a higher temperature.